Now, the other thing that we want to look at is what happens to the vapor pressure when you have a solute in there. Does the solute interfere with vapor particles being able to get out of the liquid? And as you might expect, in some cases it does. Okay, so in general, if you have a non-volatile solute, non-volatile means that it's not going to convert to vapor very easily. Okay, it's got very high IMFs. So if you have a non-volatile solutes will lower the vapor pressure of a solvent. The dissolved solute particles actually prevent solvent particles from getting to the surface. If they can't get to the surface, they can't get out. And so these non-volatile solute particles get in the way, and they kind of prevent molecules from getting to the surface, and therefore fewer of them will turn into a vapor, and you'll have a lower vapor pressure. So there's less solvent that can escape into the gas phase. Okay, this is governed by something called Raoult's law. Raoult's law is this: the vapor pressure of a solution is equal to the mole fraction of the solvent times the pure vapor pressure of the solvent. Okay, so the mole fraction is, we already know how to calculate that, and P solution is usually what we're finding, and P with the degree sign solvent is going to be given to you. It's the vapor pressure of the solvent under a particular temperature. This actually creates a linear graph if we look at this, where we have the mole fraction of the solvent versus the solvent vapor pressure. The slope of this line is the pure vapor pressure of the pure solvent. Okay, so it's a linear relationship. It's very simple to use. Here's an example. We want to find the vapor pressure at 25C for a solution where we've dissolved 158 grams of sucrose into 643.5 milliliters of water. Okay, the density of water at 25 is 0.9971 grams per milliliter. We're going to need that to figure out the mass of our solution at some point. And then the partial pressure of water, vapor at 25C, so the vapor pressure of water, is 23.76 torr. You can look that up. Okay, so let's take a look and see how we do this. We're going to use Raoult's law to figure this out. Okay, first thing we want is the mole fraction of the solvent, water. All right, so the first thing we need then is the number of moles of water. Well, we have the volume, 603.5 milliliters, and we have the density, which will give us the mass. And then we can divide that by molar mass to get the number of moles of water. That same value goes down below so that we find the moles of water, but then we need the moles of sucrose as well. That's 158 grams of sucrose divided by its molar mass, 342.3. Add those together, do the division, and you get a mole fraction of 0.9872. All right. Now, the 0.9872 is multiplied by the vapor pressure of pure water at this temperature, 23.76, and you get 23.46 torr. So look at what happened to our vapor pressure. It went from, in pure water, it would be 23.76. It went down a little bit to 23.46. That means that sucrose is a non-volatile solute. It prevented the water molecules, as many water molecules, from getting to the surface. Now, an ideal solution is a liquid solution that obeys Raoult's law. Okay, when the solute and solvent are very similar, you get nearly ideal conditions. Now, what about volatile solutions? Okay, if both components are volatile, then we need to figure out the vapor pressure of both of them. Okay, remember, the total pressure of vapor over a liquid, a mixture, will be the sum of the partial pressures of the components, PA plus PB. Well, if we're dealing with a solution, they're going to affect each other, and so we have to use the mole fraction of A times the pure vapor pressure of A at this temperature, and the mole fraction of B times the pure vapor pressure of B at this temperature. Okay, so PA and PB are partial pressures under these of these particular components. And then with the degree signs, that's the vapor pressure of the pure A and pure B if they were never mixed. Okay. Now, it's possible to deviate from Raoult's law. Sometimes you'll have a solvent and solute that attract each other. So acetone and water, for example. Okay, acetone and water are attracted to each other. They both have the ability to hydrogen bond. And so that means that the vapor pressure that we observe is going to be lower than we predict, because we're not taking into account the fact that they're attracted to each other. If they're attracted to each other, they're not going to let each other out of the liquid very easily, and you're going to have fewer vapor particles above the liquid. Okay. The other possible possible deviation would be a positive deviation. Ethanol and hexane. They're not really attracted to each other at all. Ethanol is polar, hexane is nonpolar, so they're not really going to affect each other at all. That means that some of the hexane might get out into the vapor more than you would expect. And so the observed vapor pressure, what you measure, would be higher than you predicted because there's actually more particles of vapor up there than you thought there would be because of the weak interactions between the two. So there's a lot to think about in terms of Raoult's law. It's not very difficult to calculate, but you have to kind of consider what's going on with the particles of solute versus the particles of solvent. Are they attracted to each other? What's happening there? And you kind of have to get things sort of situated in your head. Sometimes it's helpful to draw a picture to help you figure it out a little bit better.